Hello, everybody. Welcome to the Tokyo College's online event. I'm Haneda Masashi, director, and today's moderator. Today's lecture's topic is rewiring neural circuits through language. This is an exciting and timely topic since we are discussing a lot about the appearance of highly developed generative AI like ChatGPT nowadays. Today's lecturer is Professor Alexandre POUGET. Professor POUGET is a professor at the University of Geneva, and he started his study on neuroscience and biology in Paris and got his PhD at University of California, San Diego. He taught in a couple of universities in the US and then moved to the University of Geneva in 2011. Since then, he has been a professor at the Department of Neuroscience in the University of Geneva. This time he's conducting cooperative research works, especially with researchers at International Research Center for Neurointelligence at the University of Tokyo, IRCN, while he keeps a very good relation with researchers at Tokyo College and conducting a very interesting interaction of interdisciplinary research. So we look forward to listening to a very interesting, exciting lecture by Professor POUGET. Professor POUGET, the floor is yours.
Well, thank you so much, Dr. Haneda and Tokyo College for hosting me. It's been really absolutely amazing couple of months here in Tokyo. Unfortunately, I'm nearing the end of my stay here, but indeed, I've been exposed to so many different research topics and laboratories in the last 2 months. It's been really, really amazing. Today, I want to tell you about one of the projects that's taking place in my lab, which indeed, as the title indicates, is a neural model of two of the most astonishing feats of the human cognitive system, namely our ability to perform a task just based on the instructions that we're given, either verbally or written instructions, but language-based instructions that we're given. We take that for granted that we can be told how to do things and we do them, but it's actually it's unique to us. No other animals, of course, have this system, and it's an incredibly powerful communication system. And I'll talk about the reverse function as well, which is how you can learn a task, and then after you figure out how to solve a task, then express with words how you solve that task so that you can communicate that to another person. Now, you might wonder why there's this picture here. Dr. Haneda was wondering whether this was me, and I was joking that this looks like me on Sunday morning after a heavy night of drinking, but it's not me. It's actually the grad student Ryder Rivland who performed the research. So while I'm the one presenting here, it's really all his research. Okay, so in neuroscience, we're interested in understanding the neural basis of behavior. And so when we study animals, the first thing we have to do is we have to train those animals to perform interesting tasks. Here you're seeing a video of a rat learning a very simple task. The rat has to poke its nose in the middle right here. It smells an odor A or odor B. If it's odor A, it has to go to the right to collect a water reward, which is what it's doing now. And it's odor B, it has to go on the other side. It's a very in fact, so simple that if I were to tell you how to perform the task, you would perform it right away. But with animals, we cannot talk to them. So the way we train them is by providing positive and negative reinforcement. Here it's positive reinforcement in the shape of a water reward. And so it takes typically weeks, if not months, to train animals to perform a task as simple as this. Eventually we can do it, but it takes a long time. You might say, oh, that's just animals. Artificial systems, especially the new wave of artificial systems, are much, much faster. So here's an example. This is a neural network that was trained to play those video games that you're seeing here. The oldest among you will recognize it. This was the games that were developed by this company called Atari in the 80s. And what they did is to successfully train neural networks to play those games. And what's remarkable is that those neural networks We're trained not by being told what to do or how to play the game, but just by being told whether they won or they lost a particular game. And through that process, they can learn to play. And what you're seeing here on the side is what we call a learning curve. It's the performance of the network as a function of the number of training cycles that the network goes through. And you can see with the top curve, for instance, is going to 200%. 200% means it's twice as good as a human being. It's better than a human being at this game. And if you look at the x-axis, you might think, oh, 200 frames, 200 training cycles. It's not that much to get this amazing performance. But if you read the fine print, you quickly realize that what they're talking about is 200 million cycles. This is basically equivalent to several hundreds, if not several thousands of years of playing those games continuously, if you were to have a humans play this. So it takes an enormous amount of training to get those systems to perform well. And again, this stands in stark contrast with what we can do with humans. I can bring you in a lab, sit you in front of the screen, and then tell you something like, respond in the direction of the stimulus presented with highest contrast. And then a second later, I show you this display, and I think all of you will know, oh, okay, I need to move in that direction. That's the stimulus with highest contrast. And you would do that with zero training. This is what we call zero-shot learning, meaning there is no learning. You get it right away. And that's what language allows us to do. We give them some instructions, and we perform the task, right? It's so natural that we forget that in animals, we would have to go through this painful training. And so language is completely bypassing this training that would be required otherwise. So we, in my lab, in fact, ever since I was a grad student, I really wanted to understand this and understand the neural basis of this function. But when I was grad students, there was no neural model of language processing. So we didn't really know how to address this extremely complex questions. But times have changed. In order to tell you a little bit about how we approach this question in my lab, I need to give you a bit of an introduction to about how we model the brain. I realize that not all of you are neuroscientists, so I'm going to give you a very quick introduction to what we call computational neuroscience, but which is also the basis of modern artificial intelligence, and what sometimes you may have heard under the name of deep networks or deep learning. But first, a quick recap of how the brain works. I don't need to explain to you that much, as you will see. What's the brain? The brain is essentially a massive network of neurons that are connected with one another. When I say massive in your brain, it's about 70 to 80 billion neurons. Each neurons connect to other neurons through a cable. This cable is called an axon. And the axon makes contact onto other neurons through a structure that we call a synapse. Now, neurons communicate by exchanging little electrical impulses that we call action potentials. Those electrical impulses, when they're generated in the soma, in this part of the neurons, they can travel down the axon to the synapse. When they get to the synapse, they trigger the release of chemicals we call neurotransmitters. And what those neurotransmitters do, depending on their identity, is increase or decrease the probability that what we call the postsynaptic neurons will itself trigger an action potential, which will then be sent to more neurons down the line. And it's a synapse here that basically determines what the system is computing. The strengths of the synapse determine how much a neuron influences another neurons. And most of learning, as far as we can tell in your brain, come from adjusting the synapses so that the resulting network perform the task that you're interested in performing. Here's a little video that just illustrates a little bit this process. You see the action potential traveling along the axons of the neurons, and they get into the postsynaptic neurons, which eventually then itself can send more action potential. Now, this sounds a bit crazy, but that's all you need to know about the brain in order to understand what we do in my lab and artificial intelligence in general, modern artificial intelligence. So let me explain to you how we can use those principles to perform computation. Say you want to build a neural network that can distinguish between those two images, the image of a 1 and the image of a 2. How are we going to do this? Well, first, we need to take the image and turn it into a pattern of activity across neurons. Okay, so we effectively here, we're going to build like an artificial retina. This part here, it's like what's in the back of your eyes. It's a 2D layer of neurons where the neurons respond in proportion to the pixel level at their location, at their respective location, right? So if I see a 1, then those neurons here activate on this map. All right, next we're going to wire those neurons onto what we call an output neurons. We're going to make sure that this neurons is specialized in recognizing number 1. And the way we do this is quite simply by connecting all the neurons that responds to number one to that output units. And just to make the presentation simpler, instead of showing you all the wires, I'm going to represent all the blue connection as this blue triangle, and the neurons that are connected to the output neurons are indicated in the same color blue. So you can imagine now that if I present a 1 in this image, then I activate all the blue neurons, which in turn activate the output neurons, and my neurons respond. In contrast, if I present number 2, which only activate 2 of the blue neurons, then I got a much reduced activation of this output neuron here that does not respond to the 2 effectively. All right, so we can follow the exact same principle to build a unit now that's specialized for a 2. We're going to connect all the neurons in input layer that respond to number 2 to this output neurons, right? Such that if I present the number 2, then I activate very units here, and not so much number 1 units because it doesn't have the right connections. If I present then the number 1, you can see that the number 1 only recruits 2 of the red neurons. So it's not going to activate much this unit here, but we saw before that it is activating the number 1 units. All right, so we've just built a neural network here that has the ability to distinguish between the image of a 1 and the image of a 2. This kind of networks were called perceptron. They were invented in the 40s, but they were popularized by an American psychologist known as Rosenblatt, who in 1961 did something really interesting. He started working with this kind of architecture, but instead of wiring the network by hand, he's going to actually train this network to discover on its own what are the right connection in order, for instance, to distinguish between a 1 and a 2. So how do we do this? How can you learn the appropriate connections? All right, so here's what he suggested. He said, look, start with random weights. Just connect randomly this layer onto those 2 neurons here. Then present the image of a 1. And then calculate how much this activates those 2 output units. So right now it's random weight. So let's say just by chance, it happens that the number 1 activates more of the units 2 than it activates the units 1. That's not good. That's not what you wanted. What you wanted is strong activation of 1 and weak activation of 2. Okay, no problem. What we're going to do now is compute an error. We're going to look at the difference between what we desired and what we actually obtained, right? And then we're going to wiggle the rings here. We're going to adjust them a little bit so as to minimize, so as to decrease this error. It's known as gradient descent in mathematics. It's a very simple procedure, right? Because if I keep doing this, my error is going to go down and down. So I do that after presenting a 1. And then I present a 2, and I do the exact same thing. For the 2, the desired pattern, this one, different from before. I look at the difference, I wiggle the weights a little bit. And then I present a 1 again. And I keep doing this over and over again. And you can prove that after a while, the system will actually converge on the solution to this problem and will recover the connection that I set by hand earlier in this talk. So this was a remarkable achievement, but not quite what we wanted to really get neural networks to do interesting stuff. And why is that? It's because if we stick with recognizing handwritten digits, like here, from 0 to 9, then the problem is that numbers never quite look the same depending on who write them, and even you, when you write them, there will be some variability. So what we would like to have is a neural network that can distinguish between those 9 or 10 different digits, regardless of how they're written, by who they're written. So how do we do this? So here's the problem. I've got a very nice unit here, number 2, that can recognize this number 2 here. We just saw how that worked. But say I present now this number 2 in black, right? It's a slightly distorted version of the original number 2, but it's distorted in such a way that suddenly it barely recruits any of the red neurons. So I don't have much of an activation here. So this unit fails to recognize this distorted 2. What if I present the right number 2, but at the wrong location? Where there too, I won't get much of an activation of this number 2. So how do I deal with this? Well, it's going to sound a little dumb, but what I'm going to do is I'm going to develop specialized number 2 detectors for each location on my retina. So here I've got 2 of them. And I can also have specialized detectors for distorted version of number 2. So I'm going to have a lot of those specialized number 2 detectors, and I'm going to make them converge on the 3rd layer. So now my output is the 3rd layer here, which is this unit which responds whenever one of the units below responds. So then it responds to 2 regardless of where it appears and how it's being drawn, right? And for good measure, I can do that for all possible digits between 0 and 9. And we know that the more layers we're going to put between the input and the output, the easier it's going to be for the network to find solutions that are invariant to this change in position and change the shape of the actual numbers. So that's the kind of architecture that we want to use, network with multiple layers. By the way, this is what we call deep networks nowadays, network with more than 3 layers, effectively. So here there is like 4 such layers. So now we have a bit of a problem, though, for learning, because we have those layers in between. So here you have the input layer, here is the output layer, but in between we call that the hidden layers. And what's the problem? Is that we don't know how to adjust the weights in there. And that's what happened in 1961 when Rosenblatt was publishing his perceptron. He didn't know how to adjust weights in there. And the reason is the following. If I present number 2 here, I know what I want in the output layer. I'd like the unit label 2 to be very active and the other one to be inactive. But what about in the middle here? What should be the desired pattern of activation? So that stopped people for 20 years. But in 1985, this was finally cracked. Or rather, the problem had been cracked 20 years earlier, but people had not realized that they could apply it to neural networks. And the 2 people who realized that they could apply the solution to neural networks are people you may have heard about because there are a lot in the press nowadays. It's Yann LeCun and those 2 guys, David Ormerhard and Jeff Hinton. David Ormerhard passed away 10, 15 years ago, but Jeff Hinton, you probably have heard about him. He worked for Google up until about 3 weeks ago. He left Google and immediately called all the newspaper to announce the end of the world because AI was going to take over. Making it sounds like a joke, but that's literally what Jeff believes, that at this point in time, AI is becoming a serious threat. But in any case, back to 1985. In 1985, those 2 guys independently invented an algorithm that's called the backpropagation algorithms. And the backpropagation algorithms is a way to propagate this air signal that we have for the output layers onto the hidden layers. I won't go into the details. If you're a mathematician, I can tell you it's just a chain rule in calculus. It's as simple as it gets. It's really not a very complex concept, but it works. It works really well. And in 1989, it was already working. So Yann LeCun in 1989 published this paper, a seminal paper, that actually managed to recognize handwritten digits, regardless of who is writing those digits, at level equivalent to the human performance at recognizing those digits. And this network that he used was 5-layer neural network with about 1,000 units and about 10,000 connections. Keep those numbers in mind. They're going to come back because we'll see the difference between what we're doing in 1989 and what we're doing now. This was so good that he sold the system to all the banks in the US so that they would use it to read the amount written on a check by hand. So this was kind of the first application of AI at the time. Okay, so 30 years, we're now in 2023, and you've all heard of neural networks, in large part because last November, it was very recent, OpenAI, a company, released something called ChatGPT. What is ChatGPT? ChatGPT is a massive neural network, but there's nothing new in terms of the principle. It's exactly what I just explained to you. A bunch of neurons interacting with one another, trained through backpropagation. They introduce a few twists to it, but nothing really major. It's just way, way bigger. And so this big box here represents this neural networks, which has all those units. And what do they train this neural network to do? They train it on just predicting what is going to be the next word in a sentence. That's all it does. So for instance, say you're currently working with this sentence, famous sentence that Armstrong, the American astronaut, uttered while he was stepping on the moon, and he said, "That's one small step for man, one giant leap for mankind." So, okay, great. We put that into GPT-3, put the first word, that's. We enter in there, and we want the network to basically predict that the next word is going to be one. Then once we have the one, we put in the input, and now the input is that's one, and we try to predict that the next word is going to be small. And then we keep going like this, predicting the next word. We do it for the sentence, and then we do it for every sentence we can find on the internet. That's what OpenAI did. It's absolutely insane the amount of data that they used for this problem, but they did that for months and months, and they made the thing bigger and bigger. And eventually, what you get is a system that can now dialogue with people. It can answer questions, because you can put a prompt in there, a question, and what GPT-3 will do is generate the next word. So you put the next word back in the input with your questions, and then it generates the next word. And this way you can unfold the response of the network. And that's what GPT does. You know, when you go on ChatGPT on the OpenAI, that's what it does for you. So you can have, like, in case you haven't tried it, you can go on the OpenAI API and play with it yourself. Here, I was playing with GPT-3, which was the earlier version of ChatGPT, because we've been working on this for quite a while. And a friend of mine went and started dialoguing with GPT-3, and he asked the following questions. Why does your capacity to retrieve information depend on the way questions are formulated? And then GPT-3 said, the capacity to retrieve information depends on the way questions are formulated, because the way we ask questions can affect the way we think about the world. The way we ask questions can also affect the way we remember information. I'll tell you, I have been in the field for 30 years. When I saw this first system being able to respond to a question like this, I was absolutely stunned. This is absolutely a game changer. It's a big, big transition in the history of AI, this kind of level of performance. Nobody, and I've asked all my colleagues, had predicted that this would happen. Even 10 years ago, nobody would have predicted that. It's really incredible. Anyway, my friend kept on going and said, oh, I see. When you say we, you mean who? Because here in this sentence, GPT-3 is using we everywhere. And he said, I mean people in general. So my friend said, oh, very good. Are you part of this category? And GPT said, I am. What I love about this answer is that it's short to the point. GPT-3 decides when it has answered the question. It generates a terminal signal at the end of a response. So here, GPT-3 not only gave a bit of a scary, crazy answer, but did not elaborate. We are done. AI is part of us. Okay, so this is almost all news what I'm showing you. This was a conversation that took place a year ago, which is like by AI standards, might as well be last century. They are going so quickly. The system I just told you about is GPT-3. So this is the zoo of language models that are now available in the literature right now. The circle is proportional to the size of the parameters. So remember I told you about this network that recognizing that Jan LeCun developed in '89 that was recognizing handwritten digits. It had about 10,000 parameters, right? GPT-3 is 175 billion parameter. That's ChatGPT. GPT-4 that just came out is going to be 500 billion parameter, which is the case for those other systems. PaLM is the Google answer to GPT-4. It's 500 billion parameter. It's very difficult to even deal with such numbers. But this field has exploded. It made the news. We're already using it, and it's going to completely change the way we do almost everything in human society. Last May, when Google released Lambda, which is, again, a huge version of GPT-3, one of the Google engineers just could not believe what he was experiencing. He called all the newspapers across the world, and he said, we have generated a chatbot that's sentient, because he was so impressed by what the system was capable of doing. Now, that didn't end well for that employee who was fired a few days later by Google for violating Google policies. But I think actually he was indeed getting carried away. Those systems are not sentient. But I agree with this engineer that what those systems are capable of doing is absolutely mind-boggling. Okay, so back to my own research here. My lab is interested in understanding how the brain works. And about 3 years ago, when I saw the first version of those systems, when it wasn't making the press yet, I realized we finally have models that can process language to a level that would allow us to address the question I started with. How does language, verbal instructions, can allow you to perform sensory motor transformations or perform tasks in general? So you have circuits in the brain, which are actually more or less where I'm showing them here, that can get visual inputs, sensory inputs, and turn them into motor commands. So you want to reach for your iPhone that's sitting on your desk, you see the image of the iPhone, you reach for it with your hand. Those are the circuits that do that in the top of your brain. But what's remarkable is that those circuits receive connections from one inner area, particularly that's called Wernicke's area, which we know processes language and can rewire those circuits to perform the task specified by the instructions. But we have no idea, or at least until recently, we had no idea how that happens. We understand sensory motor transformation, that we have beautiful model of that, but we don't understand how language can reshape those circuits. So that's what we started doing in my lab. We built neural network that can perform those sensory motor transformation, and I will tell you a lot about the kind of tasks that we use. And in the middle, we use a specific type of neural network. They're called recurrent neural networks. They're a bit different from the one I showed you, but the details don't really matter. And we're going to train those networks to perform many tasks. We're going to start with a simple model in which the task is specified ahead of time, but not with language. It's just basically a number we give to the network. We say that's task 1 or that's task 2, but we don't give any instructions. And then we can compare those networks to this one, which has the same sensory motor architecture. But on the side here, we plug one of those large neural network model like ChatGPT that can take verbal instructions and that connects eventually onto this RNN with the hope that it's going to instruct this RNN to do the right thing. But it's all neurons. In fact, once we enter the language, after that, it's just neurons talking to one another. Okay, so what kind of tasks are we going to use? There are very simple tasks. There are tasks that are used a lot to study humans and animals. They are great because we can look at neurons in animals responding while animals are performing such tasks. One such task is called anti-go. So for instance, you get instructed to respond in the direction opposite to the stimulus. So I show you a display like this. One stimulus appears, and you have to respond in the direction opposite. So the right answer is go right because the stimulus was left. For each of the tasks, we use 15 different ways of explaining the task so that the network cannot lock onto specific word. We're going to make sure that the networks try to really understand the semantic of the instruction that's being given. Here's another task we're using. It's called decision-making task. It says respond in the direction of the stimulus presented with highest contrast. So you have to choose between 2 stimuli. So you see a display like this, 2 stimuli appear. Here the highest contrast on the right, so the right response is this. Here's another example, 2 stimuli appear. Now the highest contrast on the left, so the right answer is responding to the left, right? So that's the kind of task that we use. Another one, delayed match to sample. Response in the direction of the last stimulus if both stimuli appear at the same position, otherwise do not respond. So again, you think about this for a second, and you will perform the task right away properly. So I show you this, 1 stimulus, gap, 2nd stimulus with the same location, respond in the direction. Another trial, 1 stimulus appears, a 2nd one appears now, not the same location, right, left, so you should not respond. That's this task. Last task I want to tell you about is one that we call conditional decision making. It's one of the most complex we have in the training set. It says respond to the strongest stimulus only if you're confident, otherwise do not respond. There we go. Here's an example. 2 stimuli, clearly the one on the right has the highest contrast, we respond. Here, 2 stimuli, not so clear which one has the highest contrast, no response, right? So here the machine has to evaluate how confident it is about its response and then decide whether to respond or not. All right, so I just showed you 5 tasks, but we have 50 in our data sets. They come in different families, and we're going to train our neural network on a subset of those tasks. What we're going to do is we're going to held out 5 tasks randomly. We're going to train the system on the other 45 tasks. And when we have a language model, we'll train the system to perform the task. We'll provide also the verbal description of the task. The network gets to learn the task and what is the corresponding verbal descriptions. And then we're going to take the 5 tasks that we held out, and we're going to present them to the network along with a description of what the task is about. And what we're hoping for is that right away, the network will be able to perform the task just based on the verbal instructions, even though it has never seen this task before. First time in its life that it's seeing the task, just like human. That's what we're hoping for. And we're going to vary the 5 tasks that we held out so that we can actually test the system on any of those tasks for this kind of like zero-shot generalization. And what I'm going to show you from now on are learning curves. It's how quickly the network is learning the new task, the held out task, as a function of how many trials we use. Of particular interest is going to be the performance at the very beginning, which is what we call the zero-shot learning, right? This is how well the system is performing the task the first time it sees it. And to get a sense of what is kind of the chance level, we're going to do first this experiment with this network here, which does not have language. All right, so if you don't have language, how well would you do? The tasks that we're using, they share a lot in common. So when you see a new task, if you have a default policy that's always the same, just by chance, you'll do better than chance. And you can see here that the non-language model is already at 40% zero-shot learning. So we need to measure all our performance. How much better do we do when we have language, right? Okay, So 3 years ago, when we started this project, we didn't have ChatGPT. We only had GPT-2, which was 117 million parameters. Already pretty incredible for the time, very impressive. And when we got started on this and I convinced my students to do this, I was absolutely convinced that this is all we needed for this. So I expected this to just shoot up to whatever, 85% correct, 0 shot. To our dismay, GPT-2 gave us a little bump in 0 shot learning, but only to 55%. So our colleagues around the world say, hey guys, you're already behind, which is the curse over my field right now, is that every 6 months, the big company release a bigger network. And so indeed, 6 months later, they had a new GPT-2, which they call GPT-2 XL, and it's already 1.6 billion parameters. They're great, let's try that, that's gonna work better. It did, we got another bump in performance, but still not quite what we wanted, with about 69% correct on the first attempt. So at this point, we had tested this corner. It's every time I look at this, I myself I can't believe how quickly things are going. So we had one option, go bigger. That's what everybody's doing. But believe it or not, first of all, most of those networks are not public. They belong to the company, which is a big issue on its own. They own the technology. Second, even if they were to give us a code, I'm not equipped to run a model with 500 billion parameters in my lab. This requires specialized hardware. So this wasn't really an option. And also we thought, okay, but how about we use all neurons and think about how we want to do this instead of just go big. Indeed, when you think about it, what we want is we want a network that extracts semantic out of the sentence. It extracts the meaning. This is not what ChatGPT is trained on. ChatGPT is trained to predict the next word. And as a side product, it has semantic, but that's not really what it's trying to do. Okay, so then we went for this architecture. It's called ClipNet. ClipNet is 2 networks. One that's going to process text. Here you have a network. And one that's process images. And both networks has output layers, as before, in all the network I've shown you. And we're going to use what's called contrastive training to train the system. That is, if the description here corresponds to the image, we're going to train the system to produce similar outputs. If the image does not correspond to the description, we're going to train the system to produce dissimilar output. There's a very easy way to do this, and that's what we're going to do. That's what those guys did, because this is not my work. And so those guys did that, and we took their off-the-shelf text encoder here, neural network, and used that as our language model. We like that better because it's more about semantic now, right? It's the only way you can have those 2 systems to produce the same outputs is if they understand what is the meaning that's shared between the description and the image. So those systems are really geared toward extracting meaning. And that's something that we thought we should work better. So that's what we did. We took our model, and here we plugged in ClipNet. And sure enough, that worked a lot better. ClipNet got us to 85% correct, 0 shot learning, which is our best performance right now. I just want to emphasize, this is the performance of a network that has never seen the task. And that's how well it performs on the first attempt, based on a verbal description of what the task is about. Exactly like humans. Okay, so you might ask, well, how big is ClipNet? And if I put ClipNet on this graph here, it's a speck. It's 60 million parameters. So it's really tiny. And this shows us that, okay, going big, which is what AI is currently doing, is good. It's working well. It's giving us amazing tools. But imagine how much better we're going to do when we actually also put some thinking into how we want to go get those systems to actually perform interesting tasks like extracting semantic. Okay, so my lab is it's neuroscience lab, as I emphasized. So at the end of the day, we want to use this to understand how things work in the brain. So here we're going to pretend we're neuroscientists. So you know what neuroscientists do? They train animals on specific tasks. And then they put an electrode in the brain of the animal, and they look how neurons respond at different phases of the task. And then we try to understand, on the basis of these responses, how the brain solves the problem. So we're going to do something similar with the neural networks now here. We're going to, for instance, look at this neuron here, and we're going to ask, what kind of response property does this neuron have? And so we plot things like this. This is the activity of my neurons in 3 different tasks, as a function of the direction in which the network is responding. So if it responds to the right, you see that this neuron is very active. is the response is to the left, this neuron is not active. And it doesn't matter which task it is here. For the 3 tasks, big response here. But what's remarkable, if you look at 3 other tasks, suddenly the same neuron respond a lot when they respond to the left, but not to the right. So what's the difference? Well, the first few tasks were all go tasks. You have to move in the direction of the stimulus you selected. The other 3 tasks are anti-tasks. You have to move in the direction opposite to the direction of the stimulus that you selected. And so what this neuron is doing, it's basically doing exactly what you expect. It reverses its preference depending on what the instructions are. What's remarkable about this neuron is that it will do it on a trial-by-trial basis. Every trial, it will change its preference according to the instruction that is given. And so this is literally what we're now looking for in human brains. We're performing recordings in humans, single-cell recordings, just like we're doing, pretending to do in this model. And we're going to be looking for neurons like this that change their mind according to what you tell the patient. All right, so we can look at all the neurons one by one. When you do that, you get complex kind of like response properties that are not always easy to interpret, just like the one I showed you. So in neuroscience, we've now decided to take a different ways to look at the activity of neurons in a different way. So the neural network here in our simulation has about the order of 500 neurons. It's very hard to visualize the activity of 500 neurons. So what we're going to use is we're going to use techniques we call dimensionality reduction. That's going to take those 500 neurons and compress them to 3 numbers, because this way we can do 3D plots. And we're going to basically take a summary of those 500 numbers, the 500 neurons, to 3 numbers by trying to preserve as much of the variance as possible. This is called the principal component analysis, very classic type of analysis. So we do it, for instance, for 4 tasks here. We have 4 tasks. We're going to look at the activity in the middle here in this network before I start the trials, just on the basis of the instructions that are provided to the network. And so given color is one task, and different color pattern here depends on different set of instructions. What are you seeing here? What you're seeing is that there's a lot of structure in the activity in this network before the start of the trial. Depending on the task, the activity is already clustered in different part of the space. And the 4 different tasks here are well separated. This is true for the simple network, but this is true, of course, for a network that's using ClipNet. You see a lot of organization in the neural representation of the network here. But what's really interesting is what happened is one of the tasks was being held out during training. So in this case, now what you're going to see is what happened when this task is called anti-decision-making modality 1 is being held out. What happened is that when you have a non-language model, it's a mess. The blue dots, the dark blue dots, are all over the place. This network doesn't understand what this task is about, and indeed performance on 0 shot would be very bad. But this is where it's remarkable. If you have ClipNet, the dots here are being placed exactly where they should be placed, just by having the verbal instruction. What the verbal is they change the activity in this network so that it starts where it should start in order to perform the task properly. So what you're seeing here is this 0 shot generalization, but in terms of neural activity. So again, recordings in humans, either single cell recordings, or we can do functional fMRI, which allows us to look into the brain of intact brains and look for a similar kind of organization of activity in the brain of humans and see how language can change it on the fly, trial by trial. Okay, so what I've told you about so far is how to model this part of the brain that takes verbal instructions and send this information to sensory motor networks to get them to perform the required task. But in our brain, we have the opposite ability. This is due to an area that's called Broca's area, because it was discovered by the French neuropsychologist Broca, who discovered that this part of the brain here, if you have a damage in there, and this Broca worked a lot during World War I, where people were getting shot in the head and they had clean injuries to their brain, and he figured that injuries in this part of the brain leads to complete inability to speak ever again. It's very difficult to recover. It's called aphasia, production aphasia, and people cannot utter new sentences. And this part of the brain indeed receives connection from the rest of the brain. And we know that it has the ability to look at what's happening in the sensory networks and turn whatever solution is implemented in this into descriptions. So can we get neural networks nowadays to do this? And so what we did is we took our network here with the language pre-trained transformer is ChatGPT, or it's like ClipNet. It's one of those things. And we're going to expand it by adding a decoding network. It's a network that takes the activity in the RNN that's performing the task and then turn that into a verbal description of the task with words. And in particular, what we wanted to do is something that is a bit difficult to explain, but let me just go back to what would happen in the lab. I bring you in the lab, I train you on 40 tasks, say, simple tasks. You go home, the next day I come, and I show you one of the tasks, but I don't give you the verbal description anymore. I just showed you a bunch of display, and I tell you this is the right response, and another display, this is the right response. And then after a while, I'll tell you, can you tell me which task this was with words, right? So we're going to do the same thing with a network. We're going to train the network on a bunch of tasks. Then we're going to present the network with an exemplar of a task. We're going to let the network recover the semantic of that task. And then we're going to ask the network to produce a verbal description of that task. So we can do that. We have algorithms for doing, and we did. And to our delight, we got very nice performance on that. We got the network to produce all sorts of description of tasks. But how do you know those descriptions are any good? So this is a confusion matrix. This shows you here in this part of the matrix. It's basically, we ask how many of the instructions that the network produced were part of the training set that we use. So when we train the network, we use a specific set of instructions. And we found that 50% of the time, the network is just reusing one of the instructions that it was given in the first place. But 50% of the time, and this is column here, it produces brand new utterances, brand new way of describing the task. And so we're wondering, are those any good? So you could ask somebody to code this, read it, but it's very subjective. So we thought there's a much cooler way of doing this. We're going to take a network like this, which we call agent one. It sees a task. It says exemplar of a task. It's not being told what the task is about. It just sees exemplar. Eventually it says, ah, that's a task in which I have to respond with the identical orientation when prompted. And then we're going to take another network of the same type that's also been trained on processing of task instructions. And we're going to feed the instruction generated by the first agent onto the second agent. And we're going to see whether the second agent can actually indeed perform this task. So we basically get a network to talk to one another. And I'm very proud to say that I think we're the first one in the world, before the GAFA, to have trained neural network to use language, plain English, to talk to one another. Now, does that work? So the first thing you can do is you can pre-train those two networks on 50 tasks and then test agent one on one of those 50 tasks and see what agent two does. So these now tasks that are known to both agents. And when we do that, we get 91% correct performance for agent two based on instructions given by agent one. How good is that? Well, what you should know is that when we train those systems, we train them to be 95% correct. So here we have a little drop in performance, but not much, 4%, right? So the agent two performs almost as well, whether the instruction comes from us or comes from another neural network. What happened if the task that we're currently considering was unknown to agent two? Agent two had never seen it, never performed it, never been trained on it, and is being instructed by agent one. Then performance drops to about 80%. But remember, this is zero-shot generalization we're testing now. This is what we're testing before. And the best we could do was 84%. Okay, so we're down to 80%, but that's only a 4% drop from what we're getting when we are providing the instructions. So providing the instruction by the first agent barely results in any drop in performance. Okay, but how about the novel instructions? Because here I'm using all the instructions, but how about just those one that the network had never seen? Are they any good? And what we see is that if we limit this analysis just to the novel instructions, we see a tiny drop of performance, but again, not much. So this works even when agent one starts being creative and just produces its own instructions. All right. One thing you may wonder about at this stage is, why use language for communication when it comes to artificial systems? Those systems have similar architecture. This red layer here, which is the output of the language system, is what we call the instruction embedding layer. It's basically the layer that encodes the semantic of the instruction, which is eventually going to be fed into the neural network here. Since those guys are the same architecture, why bother through language? Why not just take the instruction embedding of agent 1 and copy it straight into agent 2? That sounds like a strange way to go, but that's what Neuralink, Elon Musk's company, claims they want to do. They want to bypass language and connect your brain with my brain directly and get them to talk to one another with spikes, which is not a crazy idea because that's what's happening inside your brain. How does, for instance, the two hemispheres talk to one another, your right and your left hemisphere? They do so by exchanging spike. They don't do so by talking to one another. And so this looks like a promising, much more efficient way for communication. Well, it might, but there will be a problem. What I can tell you that when we do this in our hands, performance dropped to 40%, which is chance. If you remember, that was as good as it gets for effectively a random system. So what's the problem here? Well, the problem is that those two agents were trained separately. They have similar architecture, but they found slightly different solutions to the same problem. And so this instruction embedding here, when I fit it in here, it's the one from the other agent. And agent 2 would have used something slightly different. And so it doesn't know what to do with this. In order for this to work, I would have to retrain agent 2 to learn to interpret what's happening with agent 1. In your brain, that's what happens all the time. Your left hemisphere learns to interpret what your right hemisphere says with spikes all the time. You've done that all your life, so it works. But if we're going to do it between individuals, that's going to be a bit different. Right, so I'm at the end of my presentation. What I was trying to show you is how you can get ultra-fast learning with ClipNet, how you can instruct networks to perform specific tasks and even get them to do zero-shot generalization. We saw that this kind of network developed abstract neural representations that reflect the semantic of the tasks that they're being faced with. We also see that there are neurons in the brain that have preferences or response property that can change on the fly depending on how you instruct the system. And at the end, we reverse this process and now started training networks to actually describe with words what they're doing and using this to communicate with one another to cooperate. So what you saw here is the first attempt, as far as I know, of trying to model the full architecture of the brain with the two major brain areas, the one doing language comprehension, the one doing language productions, and how they interact with the entire sensory motor system. Thank you very much for your attention.
Well, thank you very much, Professor POUGET, for your very stimulating, interesting talk. At the end of your lecture, you mentioned the possibility or potential of direct neural communication without language. I was shocked a little bit to hear this, because you know that as a historian or as a researcher in the field of humanities, the language is very important. Language is the basic tool to discuss or to examine or to make research, everything. But without any language, how can we be a researcher in humanities? This is a fundamental question. This fundamental question for researchers in the field of humanities. But anyway, this is just my response, reaction, just after listening to your very interesting topic lecture. And today we have a researcher, early researcher, Dr. Maria TELEGINA, project assistant professor at Tokyo College. She's also in the field of humanities, an expert of cognitive linguistics, and a leader of a research group, Language and Identity. I'm not quite sure if she shares the same concern with mine, but anyway, let's listen to her reaction, comments. But before that, I would like to stress the audience to send us any questions, comments by using the Q&A button just below on your screen. You can ask us not only in English but also in Japanese. Please send us a lot of very interesting questions and comments. And so far as we have some time, some free time, I will transfer these questions and comments to Professor POUGET. Well, now it's your turn, Maria. Please start your comments.
Yes, thank you. Thank you very much for your exciting lecture, and Haneda-sensei, thank you very much for your kind introduction. I would like to start my commentary with a confession. I believe that the language will stick around for some time. And today, as I'm a linguist, I am focusing mostly on cognitive and social linguistics frameworks. I will be commenting and asking questions from these standpoints. And to summarize the contents of my brief comment today, first of all, I would like to position my questions in this, and in this context, say a couple of words about interdisciplinarity and collaboration in the fields related to language. Then I will ask a couple of questions I'm most interested to know the answers to in order to understand more about the nature of the studies Professor POUGET was talking about, and about its interdisciplinary and collaborative features. So I would like to begin by positioning my questions through discussing the fields of study in which language is one of the keywords, whether it's the main subject of investigation or just a mediator, or sometimes a tool to achieve other theoretical or empirical goals. As far as I understood, the studies that you were talking about today are highly interdisciplinary in its nature. There's a visualization to broadly show the intersection of different areas of the study. And well, as the viewers can see here, we can consider that at very least 3 disciplines, computational neuroscience, cognitive science, and artificial intelligence are involved. And please correct me if I'm wrong, if there are many more disciplines, so if some of these 3 are not involved. And these studies are driven by linguistic or verbal tasks. And the keyword of language is typically associated with linguistic, right? Language comprehension and competence in humans are also typically subject for linguists working with natural language materials. But here, within the discipline of linguistics, we can see a lot of subdisciplinary division, as well as interdisciplinary collaboration. And this visualization is just one example. We can, for example, assume that historic linguists here would collaborate with researchers in different branches of history. Or I assume that, for example, computational neuroscience would have the most interaction with within linguistics with computational linguistics or with psycholinguistics. And my specialization is not even in this picture. It can be positioned somewhere around social linguistics and general linguistics, but it also involves collaboration with psychology and psycholinguistics. So what I'm trying to say here is that in general, study of language perception, language in human interaction or human to machine interaction is such a big and diverse community that sometimes it seems like different subdisciplines do not interact with each other so often. It is likely that linguists working, say, in the field of social linguistics would interact more with the fields that are the closest to them, interdisciplinary fields that are closest to them, with anthropology or with social, different branches of social studies, rather than, say, with the computational linguist or with computational neuroscientists. And nonetheless, we are all working with the same system, with language and with its perception. And I believe it is crucial to create and support this wide interdisciplinary discussion. Of course, there are a lot of studies that are bridging this gap and connect with respective fields on the other side of this wide field. And I believe there are many more. These are just two examples that I have encountered as I'm working with spatiality in language. However, I believe that there are more topics that can be fruitful for interdisciplinary discussion, collaboration within the disciplines involved in language. Well, as an example from the human interaction linguistics, several major knowledge contributions can be offered for discussion, for more extensive discussion. Contextually, both socially and culturally relevant language generation and evaluation, or schematization, representation, and common sense reasoning. These are just a couple of examples that came to my mind. But in relation to these examples, I would like to ask Professor POUGET a couple of questions that will help me to understand how the models you were talking about work with language, and how your field of research interacts with some of the disciplines that I mentioned. I work, so I have two slides with questions to show, and if you don't mind, I would prefer to show them first and then proceed to the discussion. So I work with mental lexicon just in two languages, and observe both intralinguistic diversity and interlinguistic overlaps. And in relation to that, I have these two questions, three questions rather. How are the instructions for models created? Is there any differentiation between languages, or how do you think what would happen with languages other than English or non-Indo-European languages? And to understand the nature of these studies that you talked about a little bit better, I'm curious to know if any collaboration outside of the range of the disciplines the study was conducted in or the studies were conducted in is possible? And is it timely or necessary at all, in your opinion? Okay, thank you very much. That's it from me.
Okay, thank you very much, Maria. Your comments and the 4 questions. So it's your turn, Professor POUGET, to ask to answer a question or some comments, make some comments to her comments.
All right. Except that you're being tough on me. It's a memory test. I have to remember the 4 questions. Is there a way you could see the slides again?
Yeah, sure.
Memory is a very important task of brain.
Yes, yes. Unfortunately, with aging is not kind on memory.
Using language, anyway.
Actually, I'd love to come back to your comments after, but maybe we'll talk to
of course,
address Maria's question first. While you're redisplaying or sharing your slides, Maria, I can start talking at least about the what you mentioned at the beginning and the importance of collaborative research. It's actually one of your questions. Let's start with this. How are the instructions for the model created? Okay, very embarrassing answer. This is probably what the toughest part of Ryder, my student's thesis, is that he started 3 years ago, and we immediately realized we have to come up with many different ways of saying the same things if we want our networks to learn semantic and not just specific words. And so he himself generated 15 different ways of saying the same things for 50 tasks. That's 750 different instructions that he generated. It sounds silly because had we waited 3 years, we would go in ChatGPT and say, hey, ChatGPT, come up with 50 different ways of saying this. And we would get it right away. Isn't that crazy? But 3 years ago, it wasn't an option. And I'll tell you, we spent a lot of time thinking about how we could do it. And we had GPT-2 at the time, and GPT-2 wasn't good enough for this. So unfortunately, yes, the answer is the current model. It was done just by Ryder. Many languages, the other languages. So how do you deal with this? So again, at the time, GPT-2 wasn't dealing with multiple languages. My understanding is that in ChatGPT, you can use almost any language you like at this point. I don't know whether you can type in Japanese or not, but I've tried in French and it does a great job. And in a way, what we're trying to extract from language, actually, in our case, is really semantic, precisely the part that's supposed to be language independent, assuming there's such a thing, which is something that's heavily debated in linguistics, from what I understand, is whether the form really constrains the meaning. But in our task, we would want to be in that domain in which a semantic is independent of the language. So we could easily use the new Google Translate system that they're using, that I know is trained on many, many, many languages at the same time, go through a common bottleneck that's precisely about semantic, and then expands back into all the languages so that you can do all the pairwise one. There's really, we could easily do this with the current architecture. Then you had 2 other questions. Okay, so here we're diving into something that's quite critical. So as I mentioned, I wanted to do this during my thesis. So we're talking late 80s, early 90s. I wanted to study this. For those of you who know a little bit, Maria maybe will ring a bell, but there was a philosopher at the time that was called Jerry Fodor. Jerry Fodor was one of the dominant philosophers at the time in the study of neural study of language in particular. And interestingly, it's the first scientific talk I heard in my life. I was an undergrad and I went to see Jerry Fodor. He was a force of nature, very, very brilliant, quite aggressive American philosopher. And at the time, the neural networks were appearing. Remember, 85, backprop is being discovered. Everybody's training neural networks. And Jerry Fodor was going around the world with a talk whose title was, why is connectionism a bad idea? And connectionism was the name we gave to this neural network approach to the brain. And his argument was like, this is exactly the wrong approach to study language and to study thinking in general, those neural networks. And I remember as a student, I listened and I thought, she's making some really interesting points. And I think he's correct. And plus the system we have now cannot do the job. And so for years, none of us really dared doing this. But things have changed. And one of the arguments in the neural network people were saying is saying, no, we just have to go bigger and eventually it will work. And ChatGPT is showing that, I don't know whether it's language, I don't know it's language like it is in humans, but it's starting to approach and have some of the remarkable properties of human languages. And scaling up was the key. And so now we have to, I think now we're ready for interdisciplinary research. Now we have to talk to linguists who have studied indeed language without worrying about the neural hardware for all those years. We have to involve the neuroscientists and the cognitive neuroscientists who know how to study language from a behavioral perspective and already had a kind of rough sketch of what it looks like on the surface of the brain thanks to fMRI and techniques like this, and talk to people like my lab that have been thinking about principles of computation in the brain in general. And on that, I just want to actually make one more point, which I think probably many people don't know on this call if you're not a neuroscientist. There's something amazing about the brain architecture. I cannot overemphasize this. All of your cortex, whether it's processing images, whether it's recognizing images, whether it's processing sound or touch, whether it's imagining your next trip for your vacation, it's always made of the same architecture, 6 layers of cortex that are connected in a very specific way. And there's very little differences between those different pieces of cortex. In particular, you go in Broca's area, the part of the brain that generates language, it looks exactly like the part of the brain that's processing images. To a computational person like me, it means the computational principles are the same. To Jerry Fodor, that's an enigma because he says language has nothing to do, Chomsky and those guys have said, completely different from the kind of computation involved in visual processing. I'm not ignoring their arguments. They were powerful and super interesting arguments, but the neuroscience is stubborn. It's the same architecture. So I think the challenge now is to really try to tackle this now that we have the tools and reconcile all of this. And I just want to finish on Noam Chomsky, who is the godfather of all this, created all of modern linguistics, or at least one version, but I guess the dominant version. I hope, Maria, you agree with me. But he had an article in the New York Times 2 months ago or months ago, in which he strongly reacted to ChatGPT and continues to call it a statistical parrot. I think it's a word that he's using. I think that's a wrong attitude. I have immense respect for Chomsky. I hope he's not listening, but I think really he's toward the end of his career, and I think he's missing the boat on this. We finally have the tools to address the question that really he was obsessed with from a neural perspective, and that's going to require a dialogue like we're having now.
Yes. Wow. Well, thank you very much.
You have any reaction from Maria? You just agree with him, or?
Yes, I agree that this is the moment when we have to try to. I think my probably initial thought was that yes, this is the moment of development where we need to try to actually collaborate within the whole field of studies that are related to language and language perception to understand what it means, what is happening with artificial intelligence today. So I can say that I absolutely agree with Professor on that. So, yes, thank you very much for the answers.
If I may, I just add a word to this. There's a very healthy and vivid debate right now going on what's going on in those large language models like ChatGPT. Jeff Hinton and Yann LeCun, the 2 people I mentioned, are on the news every day discussing it. Nobody agrees on what's happening in those systems. Yann LeCun would say it has a little bit of understanding, but those systems don't really understand. Jeff is more of the position of like, no, this is a deep understanding of semantic in the system. So I'm just mentioning that those are 2 leaders. They got the Turing Prize for their work, and they can't agree on that. And just 2 days ago, they were saying, we got to come to a consensus on what those systems are doing, but it's going to be tough, complicated, but very exciting. It's really one of the most exciting times in my career as a computational neuroscientist. All right, so I'll get going. The first question from Lydia Shamova is asking, thank you for your lecture. I would like to ask about the role of the nucleus codatus. I think codates is what you mean. I hope that's what it is. When choosing language in bi-multilingual or even choosing the words of the same language. My question is this brain system reproduced the same way in AI? And the answer is no. AI right now doesn't care too much about the neural architecture and the brain architecture beyond just the fact that it's just a big neural network with neurons talking to one another. And frankly, I'd say we're still very unclear about the role of, so the codate, for instance, is a part of the brain that sits under the cortex, called what we call the basal ganglia. And I think it's very much debated exactly what kind of computation is performing for language. But the kind of things we're doing now in our field is we take this transformer networks, those big language model, and we try to map them onto the brain architecture. Those are the early days, but I think that's how we're going to answer the question that you're asking here. So stay tuned. All right, so I'll keep going. Second question is from Trent Brown. Some anthropological studies show that the apprenticeship for highly complex manual tasks often involve very little, if any, verbal instructions. Learning mostly occurs through observation, physical scaffolding, mimesis, and trial and error. Similarly, people highly skilled in complex manual tasks often struggle to verbally articulate how they do what they do. Based on your research, are you able to offer a neurological explanation of why this might be the case? A very, very good question. So my research is not that relevant for this. What we know already is there are two memory systems. One has to do with learning skills, and the other one has to do with learning more like facts and reasoning. And so language is definitely more connected with the latter. Skills are things like you want to learn to ski or manual task. And indeed, for those, language is not very good. You can tell people, you can help them, you can correct things, but unless you do trial and errors, you won't get it. So we know that's a fact of learning those kind of things. So we don't really expect that language will have a huge impact on this. The kind of simple tasks that I was showing you today, those are more like properly tuned for language. So indeed, this distinction exists, it's in the brain. It's to the point that if you suffer from damage in a place of your brain that's called the hippocampus, you will still be able to learn to ski, but you will never learn a new fact in your life. You will never be able to recognize a new person for the rest of your life. And there are patients like this. I highly recommend the movie Memento if you want to see a movie that deals with this. So those are really different memory systems. Thank you very much for the great talk. I wanted to know whether there was a significant difference in performance for both SimpleNet and ClipNet on the confident task in comparison to the other tasks, because it involves a second order decision to solve. Thank you very much. I'm embarrassed to say that I don't know for sure. I'm almost sure that's the case, but I don't know for sure. And the reason I'm embarrassed is that the work I showed you today is completely new for my lab. The rest of my career, I worked on exactly that task with a confidence judgment. That's what I do for a living, is understand how you take into account confidence and uncertainty when you reason about things. And we have neural models that. And that's actually why we include the task in the list. And we're pleased to see that our system can learn it, but we never went back to see the difference with a SimpleNet. But I suspect that's the case, that ClipNet is much better at that. Then we have a question from one of my current colleagues at RRCN, Mingo Chai. Presumably the training data for ClipNet are mostly discrete images, which are hard to express logic, conditional statements, or sequences. But the instructions for the task clearly should incorporate these. So I wonder if you have any thought on how representation for such type of information used in instructions can be learned by ClipNet. So I think that speaks to the fact that indeed all we did is we took ClipNets, and Mingo is right, just use some discrete images, which is not at all was trained on what we're going to use it for, and yet it works. But we're 84%. So I don't have any thoughts about how to improve ClipNet, but I think that's what we should try to do, is try to think about how to train the system so they're more in tune with the kind of tasks that we're using in this particular project. Just as a side point for Mingbo, one thing we tried is we tried to train, so we plugged in off-the-shelf ClipNets, and we tried to fine-tune it to our data set. That didn't work. That did not result in any better performance. So something there that we need to look into. Another question from Chunyan Lee. I feel like a radio host of some sort. Thank you, Professor, for the great talk. My research focuses on social determinants of human behaviors related to health. I would love to hear your insights about how we can use AI tools to predict human behaviors and how to maximize the potential language to nudge behavioral changes for good purpose. Oh my goodness. So this is really an AI questions, which goes well beyond my field of competence, but it's an excellent questions. And I can tell you that it's happening in the field. People are really wondering about this. This is going to be embarrassing because I actually met 2 months ago a French scientist who's currently working in New York for Meta, for the AI part of Meta. And if I encourage you to send me an email, we'll put you in touch with her because she's trying to exactly do this. In fact, she's trying to use AI for therapy. So she's trying to develop chatbots like ChatGPT that are going to try to help people who struggles with specific issues. And that sounds like a pipe dream, and it was 3 years ago, but she's competent for this kind of thing. That's what she's been trying to do all of her life. And she's extremely good AI searcher. She started a company to do this, and my guess is that there's really fantastic potential in this. I think the system will quickly learn what it is that you need to do to help people deal with certain type of issues. Now, often, as you know, it's the best therapy is just listening to people. That's what my kids tell me all the time because I'm very bad at that. They keep saying that I should stop talking and just listen. And I think actually those systems will actually quickly learn to do that properly and know how to just direct discussions in a way that's constructive and helpful for the person. But don't quote me on this. I could be completely wrong. I'm just maybe being really optimistic here. Next question from Keita Umejima. So far they're all in English, but if it's in Japanese, I'll definitely need your help.
Okay.
Why is human language such an efficient tool for comprehension and production? Do you have any thoughts? This actually goes back to, I think, Professor Aneda's question. Is it an efficient tool for comprehension and production? I think I would seriously question that. First of all, note that inside your brain, I mentioned that during my talk, there is a need for communication between different brain areas. They do that with spikes, with action potential, those electrical impulses. They don't go through language. The only reason we need language is because suddenly, it's a different brain. I don't have a direct connection. So evolution discovered, and only just very, very recently in the history of evolution, stumbled onto language as a way to communicate. And it's amazing compared to what animals can do. But I think we have to ask a question, can we do better? We only have like, 2 million years of evolution on language. Nothing, it's a blimp in evolution. So here's my predictions, is that artificial systems are quickly going to learn their own ways of communicating. And it might very well be the case that they're going to discover a way more powerful communication system than the one we currently have. And I'm going to offer as almost half a joke, but it's somewhat serious. Anybody who has a partner who is married knows how complex it is to communicate feeling and to understand each other. We all spent half, if not more of our time, just trying to clarify what we meant. So I don't know whether it's very efficient. I think it's actually very primitive. When the early days of language on the evolutionary scale, And I think we're going to do way better. So to Professor Haneda, I think that I'm not worried. I think that what's going to happen is this next generation of systems, they may not be humans, which we could discuss, but we'll communicate in way more efficient ways.
Very good.
Cynthia Vizzani is asking, Professor Pouget, what is your opinion on the scaling hypothesis? Are these models get larger? Will they just continue to get more capable? I'm pausing here because this is the questions that I've been debating with my colleagues for 30 years, and influenced by Jerry Fodor, who I mentioned earlier. I always thought that, you know, you need scaling always helps, but sometimes there are like basic principles that you need to implement before you can hope that things are going to get better. And I honestly thought until 10 years ago that neural network were missing some basic computational principle in order to deal with language. And I've been proven completely wrong on this. So I'm a bit worried or happy to hear that maybe scaling will be the solution and that we may have all the ingredients in hand. I'm not super confident with that statement, but certainly right now it's looking really good. I think the progress is going to come not so much from changing the architecture that we're using, but improving the learning algorithms. There's a lot there that's going to be needed, and that's not scaling. That's just being more clever about the learning algorithm. But note that, you know, with the system we have, I predict that we're going to get the current system to learn the learning algorithms. So we're going to learn to learn. And there's already people working on that. Joe Naka is asking, now that the black box that is trained, that is the trained neural network, can at least be described verbally, what are the implications for sharing a machine-generated knowledge or deciphering of human cognition? For deciphering human cognition, it's already being used extensively, those neural networks now, to help out, basically read people's mind. But indeed, I think I'm trying to understand exactly how to address your question. I think you're asking, the question is partly about this issue of interpretability. So the artificial neural networks can produce amazing performance, but we struggle to understand how they get to the solution that they find. And there are cases where explanations are needed. If we're going to have an artificial doctor who's going to look at all your symptoms and say, I think you have lupus. Well, we are going to require that the doctor explains why, and that the artificial system explain why. And indeed, I believe that having this kind of language on the side that can turn the inside of a neural network into words will be exactly what we need and will help with the interpretability of those systems. Jonaka asked a second question. If brain parts look alike, regardless of their function, could the difference be explained in terms of the spatial relationship to each other's? Definitely. So anatomy is indeed the big determinant of what a particular part of the brain computes and represents. And a lot of that is specified by the genes. So when you're born, the basic architecture is already in place and it's not going to change. It's a detail of the connectivity that's going to change. So that's indeed what's going on. We see that in neural networks. You know, if you have a multi-layer networks with lots of layers, as you go deeper in the network, it performs different computation. It represents different type of information. But the basic computational principles are the same in every layer. So it's going to be very similar in the brain. I think we have a couple more questions. One by Yanling Lim. I read that language is for communication and communication is 60% body language. So I kind of disagree that the world should proceed to assume that a world that doesn't understand emotional facial expression unspoken would be a complete human world. What do you think? Are emotions still valid or totally primal and outdated? We should ignore emotion in our communication. I'm not sure about the percent of 60% body language, but I certainly absolutely agree with your point. Body language is very important. Anybody who's run into miscommunication over email, understand that. I hate email, especially when there's a conflict. I think Professor Nida, as the head of a center, knows that if there starts being a conflict, you bring the people in the room because body language is going to be essential. And it's going to be important for artificial systems. And I'll tell you, they will take them into account. Let me give you an example. Google is currently working on ChatGPT, but for speech. So instead of predicting the next word in a sentence, it's predicting the next sound as you talk. And so what it means is instead of having ChatGPT that just produces a sentence on your computer, the next generation of system, which is 6 months away, a year away, will be talking to you. And I heard the first demo of that. It was super impressive. But the part that was absolutely wonderful is that those systems are trained on YouTube videos, people talking in normal situation, expressing emotion in the way they talk, just like I do in this presentation. And so they immediately pick up on that. So when I heard the speech that was generated, first of all, they asked a variety of questions. Like the first question was, what is your favorite sport? And the system answered, and it was a young kid. We could tell right away with the voice of a young kid responding, oh, I love playing football. And the next question was like, where do you think you'll spend your next vacation? And then it was actually a woman's voice that responded, adult women, and so on. And every time it sounded like it had like the excitement you would expect from somebody talking about their favorite sport and so on. And then the researcher was presenting this, said, this is the same system every time. We did not change it. There isn't one for a young kid, one for women. It's just that the system understands from the questions who is more likely to discuss a question of this type, and also picks up on the emotions that are specific to those questions. One thing that he said was remarkable is that the first time they trained the system, they heard breathing in the system. And they were like, what is this? This system doesn't breathe. And they realized that the system learned that breathing is part of human language. So I'll tell you, what's happening is really incredible. In 5 years from now, you're going to be talking to the computer like you're talking to a person, and it will have all the kind of right intonation. Not body language, and let's embody it in an actual body, but that's going to take longer because robotic is lagging behind right now. But it will be part of it, and no, emotions are not outdated, and they will be incorporated into the system. Just one word about emotion. I think great mistake in the general public and for many of my colleagues is to distinguish between cognition, rational thoughts, and emotion. Emotion is an inherent part of rational reasoning. When we say that somebody is emotional, what we mean is their emotions are out of whack. We mean that they're not working properly. When they're working properly, they're essential to your functioning. If you lose your ability to have emotion, you cannot function in society, right? And that's what happened with kids who have like severe autism, but also with people who lose the amygdala. So emotion is an inherent and central part of the way you function, and it's essential for cognition. How much time do we have left? We're at the end. Okay. I'm sorry. There were 2 questions left, and I apologize to those people. I didn't realize I lost track of time. Yeah. It was a bit too long. But I invite you to just send me an email. I'll be happy to just like provide you with a response. If you type my name, you will find my University of Geneva email, and I'll be happy to quickly address them.
Thank you very much, Professor Pouget, for your great effort to respond to all these questions. And excuse me, I apologize for the technical error we make, because I couldn't read any question by myself. But anyway, I now understand that the world is changing drastically and in an exciting way, very rapidly. And we will see 6 months, in 6 months, another very exciting discovery or invention soon in connection with neuroscience or ChatGPT or something related with language and image. I got a lot of new knowledge, and I need to think of all these new discoveries or new inventions by myself. And let's discuss these issues raised by Professor Pouget among ourselves. And we would like to invite once again Professor Pouget to discuss further development of this field, maybe in 6 months or maybe in 1 year. Thank you very much, and see you again soon. Thank you, Professor Pouget and Maria.